Hello everyone. In this session we will talk about interrupt processing and how to use the interrupts in 8051. What are the different registers available in 8051 for processing interrupts? What are the different types of interrupts, as well as what are the priorities of each of the interrupts and how to change the priorities of each interrupt. So coming to interrupts, in any program we can run and wait for an event either in a polling mode or in an interrupt mode. Now let me explain these two different scenarios. Now let us take an example of setting a alarm in the clock. Okay. Now say for example, if you want to set an alarm at 6 p.m. every day in the industry to switch on the siren. Okay. Now how do you do that? One way of doing it is you assign a person to keep on monitoring the clock for every 15 minutes, and the moment the clock reaches or moment the clock shows 6 p.m. he will go and switch on the siren or alarm. That is one way of doing it. Here what we have done is we have assigned a resource to monitor the clock for every 15 minutes. So the resource is busy in the process, and the resource will keep on monitoring for every 15 minutes to check whether 6 p.m. has reached or not. Okay, that is called as the polling mode, where the resource that is assigned will keep on monitoring things to trigger an event, okay, or to serve an event. Okay. Now the another way of doing the same thing is, in the clock if we have an alarm setting option, we will set the alarm at 6 p.m. and we will not assign the resource to monitor the clock. So what we have done here is we have removed the resource from monitoring the clock. Rather we have registered an alarm in the clock itself. Okay. So we are not monitoring the clock frequently. However, the moment the clock reaches 6 p.m. the alarm will trigger off, and then the person, after hearing this alarm, will go and switch on the siren. Now this is not a polling mode, because the person is not monitoring the clock frequently. Rather the person is given an indication that 6 p.m. has happened by the alarm going off in the clock. Okay, so this is called as an interrupt mode processing. Okay, now let us go to the next page and discuss about what are the different interrupts that are available in 8051 and how are these interrupts handled. Okay, so there are 6 different interrupts. They are reset and external hardware interrupts 0 and timer interrupt 0, and external hardware interrupt 1, timer 1 interrupt, and serial communication interrupt. Okay, and each of the interrupts, as and when they occur, say for example reset, when it occurs the microcontroller will force and jump to the location 0000. Okay, and this location 0000 will contain a interrupt service routine or a service routine that will handle this reset event. So as an example, whenever you want to press a reset button, then you want to clear all the registers. This is one of the operations. Okay, so the reset routine will contain some code that will reset all the registers. As an example, I am taking a hypothetical example. So similarly, if you want to handle external hardware interrupt 0, then that particular interrupt service routine will be written in 0003. Now what is the interrupt service routine? The interrupt service routine is nothing but a set of commands that are written to handle that interrupt. Okay, so the interrupt service routine is nothing but an action that needs to be executed, or action that needs to be performed whenever a particular event happens. Okay, so the reset ISR is located at 0000, INT0 interrupt for the interrupt INT0, the ISR is located at 0003, and so on and so forth. Okay, And the third column gives you the pin number. So reset is nothing but the pin number 9, and int0 is nothing but bit 2 of port 3, and int1 is nothing but bit 3 of port 3. Okay, so please remember, when I say bit 2 of port 3, it is in the third location, because the first we have bit 0, bit 1, bit 2 in port 3. So it is the third location, so we call it as bit 2 of port 3. Okay, and the flag clearing indicates whether the the flags are cleared automatically or whether the programmer has to clear it. In the case of serial interrupt, whenever the serial interrupts happens, it is the responsibility of a programmer to clear the interrupt. Okay, having talked about the different interrupts in 8051 and their location that contains the ISR and the interrupt vector table, now let us talk about interrupt processing. Okay, whenever a particular program is executing and if the interrupt occurs suddenly, at that time the program finishes the current instruction that is being executing and saves the address of next instruction that is present in the program counter onto the stack. Okay, by pushing those content of PCL and PCH. Okay, it also saves the current status of all the interrupts. Okay, and then it jumps to a fixed location in memory which contains IVT, that is the interrupt vector table, and this vector table, interrupt vector table, contains one-to-one mapping of an interrupt and the address of interrupt service routine. Okay, so from IVT the microcontroller gets the address of the interrupt service routine and then it jumps to that address to serve the interrupt. Okay, so once the ISR is executing, the last instruction of ISR necessarily has to be RETI, which states that it has to return from this interrupt service routine back to the main program. Okay, so when RETI is encountered, the microcontroller returns to the place where it was interrupted. So how does it do that? It will pop out the the PC, the content of the PC back from the stack to the program counter. So whatever was pushed from PC to the stack initially before executing the ISR will be popped out back to PC from the stack. Okay, so this is the process of interrupt servicing. Now let us go to the next topic. So in interrupts, there are two primary registers in 8051. Okay, so the two primary registers are called as interrupt enable, the short form is IE, and interrupt priority, IP. Okay, so interrupt enable is a register which will allow us to enable all the interrupts the interrupt enable register, that's IE register, will help you to enable each and every interrupt. Okay, and the interrupt priority register will help you to set the priorities of each of the interrupts. Now let us talk about the interrupt enable registers. Now this 8-bit register contains EA, ES bit, ET1 bit, EX1 bit, ET0 bit, and EX0 bit. Now EA bit will enable or disable all the interrupts. So that means to say, if this is set to 1, then it will allow us to enable the rest each of the interrupts. If it is set to 0, irrespective of the field value set in the rest of the fields, it will disable each of the interrupts. Okay, now EX0 stands for external interrupt 0. Okay, so whenever the EA is set to 1 and if the rest of the fields are bits are 0 and EX0 is set to 1, then it will enable the external interrupt 0, int 0. Okay, and if ET0 is set, okay, when EA is set to 1 and ET0 is set to 1 and the rest of the bits are 0, then only timer 0 interrupt is enabled. Okay, on a similar line, if EX1 is set to high, then INT1 is enabled, and if ET1 is set to high, then timer 1 interrupt will be set. So when we say timer interrupts are set, that means whenever the timer overflows, then this it will jump to the interrupt service routine. Okay, then ES stands for a serial port interrupt. So whenever ES is set to 1, it will enable the transmit interrupts as well as receive interrupts. Rather than saying enable, it will provide a mechanism. Whenever this interrupt occurs, it will jump to the interrupt service routine located in 0 to 3. Okay, so what is really critical in this interrupts is when the interrupts are set, so the address of the ISR plays a predominant role in serving the interrupt. So INT0 being set, whenever it is set, so whenever INT0 happens, so the program will jump to 0003. So that is something that we need to remember. Now let us go to the next register, that is IP. Before discussing about this, let us go to the IVT again, the interrupt vector table again. Now if you see these 6 interrupts and their ISR, we need to understand the priority, default priorities of each of the interrupts. So whenever a reset occurs, this is at the highest priority. Whatever may be the interrupts occurring simultaneously, if the reset occurs, that is given the highest priority, and then the program will jump to 0003. Now the IVT entry is in the order of priorities. That means to say reset is given the first priority, INT0 is given the second priority, timer 0 interrupt is given the third priority, then INT1 is given the fourth priority, and timer 1 is given the fifth priority, and the least priority by default is given to serial interrupts. Okay, so let us say that 2 interrupts happen simultaneously, that is INT0 happens simultaneously when TF0 interrupts has also occurred. Under these circumstances, INT0 being on the higher priority side than TF0, the INT0 will be served first and then TF0 will be served. Okay, because the priority takes a precedence whenever the interrupts are being served. Now what happens if at all the TF0 is TF0 interrupt is flagged, and when TF0 interrupt is being served, then what happens if INT0 is INT0 has occurred? Under this case, what happens is, since INT0 is of the highest priority than TF0, so whenever the interrupt service routine of TF0 is executing, so the program will halt the execution of TF0 interrupt service routine and jump to INT0 service routine, and then it will serve the INT0 service routine and come back to the TF0 service routine. And once the TF0 service routine is executed completely, then it will jump back to the main program. So this process of an interrupt occurring within an interrupt is called as nested interrupts. Okay, now let us go back to the interrupt priority table, priority registers. So in the interrupt priority registers, we see that there are 5 bits that are of importance. So PS, PT1, PX1, PT0, PX0. Now these are the bits that decide the priorities of each and every interrupt. Now let us say that PX0 is set to 0, or rather let us say that all the bits are set to 1. When all the bits are set to 1, all the interrupts are given the priorities, so the default priorities will take precedence. Okay. Now, if PS, PT1, PX1 and PT0 are set to 1 and PX0 is set to 0, at that time the default priority will be overridden and PT0 will be given the first highest priority, PX1 is given the next priority, PT1 is given the third priority, PS is given the fourth priority and PX0 is given the fifth priority. Now, if only PS bit is set to 1 and the rest of the bits are given the value 0, then the first priority will goes to PS and the second priority will go to PX0, third priority to PT0, fourth priority PX1 and last priority will go to PT1. So, interrupt priority register is used to assign priorities order for each of the interrupts. So, if it is set to 1, that will be given the highest priority. If it is set to 0, that will be given the lowest priority. So, PS being 1 will give PS as the highest priority. PT1 being 1 will give PT1 the timer 1 overflow event a highest priority. PX1 will give you external interrupt 1 as a highest priority if PX1 is set to 1. Okay, so on and so forth. So the priorities can be set by setting it to 1, or it can be given a lowest priority by setting it to 0. Now let us demonstrate the interrupt working using assembly language. So I'll write a simple program in assembly language to demonstrate the working of interrupt int0. Okay. So to start with, we will locate our code in 8000H. So we do that using assembly directive org 8000H and we'll say start. Let us use the start label and we will now enable the interrupt. The way we do it is move IE, comma, we have to assign some value here. If you want to enable int0, int0 corresponds to external interrupt 0, so that should be set in the lowermost bit of IE. So it is hash 00000001. So binary. Okay. So the LSB being 1 implies that the int0 is now enabled. Now along with this, we have to also enable the EA flag so that the interrupt is enabled. So the value of IE is going to be 81H or 10000001. Okay. Now having assigned this particular value in IE, we will now clear P1.5. Okay, CLR P1.5 and then we will create a infinite loop LOOP and we'll say a jump LOOP. Okay, I put semicolon instead of colon. Okay, so we are now executing in this line in a infinite way. This loop will be executed in infinite way. Now we have enabled int0 or external interrupt 0. Okay, so our objective is to show what happens whenever this particular loop is running in infinite way. What happens when int0 gets triggered? So in order to show that, we have to implement int0 interrupt, or we have to implement a interrupt service routine for int0 interrupt. So as in our previous slide, from the interrupt vector table, int0 maps to a location org 0003. Okay, so ISR for int0 is located in a location 0003. Okay, so we have to implement the interrupt for interrupt service routine for int0 here. So here what we are going to do is we are just going to complement cpl p1.5, and once we complement this, we will return back to the main program using command reti. Please pay attention, we are not supposed to write ret here, we have to say reti, because we have to restore back the states back to the original states when the interrupt was triggered, when we return back to the main program. Okay, so and also I'll end my program with the assembly directive end. Okay, so let us analyze this program again. So initially int0 is enabled, okay, and even EA by providing EA is equal to 1 and the LSB of IE is equal to 1, and then I'm going to clear p1.5, and then I'm going to run this loop in an infinite way, and when this loop is getting executed, if the int0 interrupt occurs, at that time it will jump to the ISR location 0003. There I am going to toggle p1.5 and return back to what it was executing. So since initially the p1.5 was 0, when the program is executing here and when the interrupt occurs, it will toggle p1.5 from 0 to 1, and once again when the interrupt occurs, it will toggle it back to from 1 to 0. So the interrupt occurrence is given by int0 flag. Now remember, int0 flag is mapped to bit number 2 of port 3, and it is denoted as int0 bar. Okay, the reason why it is denoted as int0 bar is the interrupt occurs when the interrupt pin changes from high to low. Okay, so let us now write one more routine here at 0 location org 000 hash, and I'll say here ljump, okay, start. Okay, so the program will jump to the start and it will keep on executing till the interrupt occurs. Okay, so let us compile this program and let us put the session in the debug mode. Okay, and we are supposed to monitor port 1. Okay, so we will monitor port 1 because p1.5 gets toggled. Okay, and at the same time we will open port 3 because p3.2 corresponds to int 0. Okay, and let me run this program. Okay, now if you see, the moment I run this program, p1.5 is cleared because we have used clear p1.5 command, and now it is running in an infinite way. Now till now interrupt has not been provided. Okay, now the moment I lower p3.2, let us see what happens to p1.5 here. I will lower p3.2 here. So if you see, the moment p3.2 is lowered, int0 gets asserted as low. At that time it will trigger the interrupt service routine, so it will keep on jumping to this interrupt service routine. So basically interrupt has occurred, it complements p1.5 and comes back, but int0 is still low, so again it will trigger an interrupt and it will go to the ISR routine and complement p1.5 from 1 to 0, and it will keep on continuing to toggle p1.5 from low to high and high to low, low to high, so on and so forth. That's the reason you see that this flags, this bit is it keeps on changing the state of this particular bit. Now in order to stop this toggling, I will just enable p3.2, that will assert int0 as high, and that will stop the interrupt processing. So once I make p3.2 as high, if you see here, the p1.5 is not toggling. Okay, I'll redo setting p3.2 as low. Okay, once I do it low, then the interrupt starts getting processed. Okay, that is about int0 processing. Okay, so now let us extend this problem further. We will serve multiple interrupts. Okay, so in order to serve multiple interrupts, we have to enable those pins of the interrupt. Okay, so currently only int0 is being triggered. Okay, so now let us enable int1 also. I'll enable int1, and then when for int0 I have implemented the interrupt service routine, but for int1 I have not yet implemented interrupt service routine. Okay, so I'll implement ISR for int1 as well. From IVT we know that for interrupt 1 the ISR should be located in 00013. Okay, so I will change this to 00013, and let us assume that when the interrupt 0 is happening, then it should toggle 1.5, and when interrupt 1 is happening it should toggle 1.3. Okay, so let me compile this particular project. Okay, and now let me go to the debug session. Okay, and let me see this particular reading. Okay, so if I see here int0 is not yet enabled, int1 is not yet enabled, and all the codes are 1. Okay, we have not, this is because we have not yet started running the program. Let us run the program. Okay, when we run the program, here EA is set and int1 and int0 is set. So if you see this particular column ENA, that stands for enable column, int0 is enabled and int1 is enabled. So that is the reason you see that it is 1 and 1. Now we have not yet assigned the priorities for interrupts. So by default, if we go to our earlier slide, okay, so the priority is in the order of the listing. That means reset is at the highest priority, int0 is at the next priority, and int1 is at the 4th priority, so on and so forth. So whenever the interrupt occurs simultaneously, int0 will be given higher priority than int1. Okay, so let us go back, and now the program is executing. So the port has been reset, all the values of the port has been reset. Okay, now int0 is provided at p3.2. now if I reset that to 0, p1.5 keeps on toggling. Okay, if you see here. Okay, now if I set p3.2, it has stopped, p1.5 has stopped toggling. Now I'll reset p3.3, that corresponds to int1. When that is reset, I see that p1.3 is getting toggled. Okay, now let us see what happens when both of the interrupts int0 and int1 are enabled. When both of the interrupts are enabled, we see that only p1.5 is toggling. This is because by default int0 is having higher priority than int1, so the ISR of int0 will execute. Okay, now let me stop this program and let me go back to the normal mode, and now let me go to the PPT and let us see the layout of interrupt priority register. In IP register, as you see, these bits, whenever I set the bits of px0 as 1, that will be given the highest priority, and if I set px1 as 1, that int1 will be given the highest priority. So in order to change the default priorities, what I will do is, if I want to have a higher priority for int1 instead of int0, then I have to set the px1 to 1 and px0 to 0. Okay, that means to say, let me repeat it. If I provide px0 is equal to 1 and px1 is equal to 1, then int0 will have higher priority than int1, as like the default priority. But if I set px1 is equal to 1 and px0 is equal to 0, then int1 will be given higher priority than int0. Okay, so if I have to give int0 higher priority than int1, then IP should be 00000100 in binary. Okay, let me set IP in this particular program. I say move IP comma hash 00000100 binary. Okay, and I will compile it. Okay, and let me run this particular program. Okay, program is running. So port 1 is now reset, and if you see here, port int0 is enabled and int1 is enabled. But if you see this priority column, PRI column, that stands for priority, int1 is given higher priority than int0. Okay, so now let me enable int0 first. Okay, we see the p1.5 toggling, and let me disable int0, and I'll provide a interrupt at int1. When I provide a interrupt at int1, then p1.3 is toggling. Now I will enable both the interrupt. If you see, in this case p1.3 is toggling. In the earlier case, when I did not assign any value to IP, I was seeing that p1.5 is toggling, whereas p1.3 was not toggling. Now in this case p1.3 is toggling, because in this case we have made int1 at a higher priority than int0. Now let us implement the interrupt using C programming. Okay, I will remove the assembly program from the project. Okay, and I will create a new project. Okay, called as I will create a new file, new item in a file, C programming item. So I'll say int external.c. Okay, I'll add to this. Okay, now a C program should always start with include. We have to include reg51, that is the register definition file .h. Okay, and CLUD. Okay, now I'll write void main void void and open the flower bracket and close the flower bracket. In the main program, I will first enable the interrupt I is equal to 0x81. Okay, so what is this? This is nothing but 0 1 0 0 1 0 0 0 and 0 0 0 1. That is, i.e. EA is high and external interrupt int0 is enabled. Okay, so that is 8 1. Okay, so now after this I will set p1 to 0. Okay, so p1 I'll set it to 0 is equal to 0x00. Okay, and then I will put my program in a infinite loop. The way I do it is, I will just have a while statement, while always true. This will put my program in the infinite loop. Now I have enabled my interrupts. However, I have not yet set the ISR routine. I have not written ISR for int0. So let us write a ISR routine for int 0. In C program, we will have to define a interrupt function. So the way we do it is void now int is 0. This is the function for handling int 0. So I will not have any parameter. Okay, then I will say that this function is an ISR routine. So the way to do it is I have to I have to write interrupt 0. Okay, int 0 is interrupt 0, int 1 is interrupt 2, and timer 0 interrupt is interrupt 1, and timer 1 interrupt is interrupt 3. Okay, and serial interrupt is interrupt 5. I repeat it. Let us go to the slide first. Okay, and go back to the IVT. Okay, so int 0 is interrupt 0, timer 0 interrupt is interrupt 1, and int 1 is interrupt 2, timer 1 interrupt is interrupt 3, and serial interrupt is interrupt 4. So interrupt 0, interrupt 1, interrupt 2, interrupt 3, interrupt 4. Okay, so having defined this particular ISR, I have to now implement what I want to do within what I want to do in this particular ISR. So what I'm going to do is I'm going to complement port 1, so that complementing instead of complementing port 1, let me now define a data type called as S bit. Okay, S bit, my pin or toggle P toggle or S wave. Let me say I want to generate a square wave in pin 1.5. S wave equals to P1 cap 5. So this is the way I assign a S bit S wave to fifth bit number 5 of port 1. Okay, so what I'm going to do here is I'm going to toggle inside the ISR the S wave, that is eventually it will toggle P1.5. okay, so I have toggled it. So let me see the program again. So I have defined S bit S wave as P1.5. then I have toggled S wave within the ISR. I have enabled the ISR in the main program, and then I have, okay, there is a small error. P1 I should I have assigned it as 0 0, and then I am running this in an infinite loop. Now let me compile this program. Okay, there are no errors, and put the session in the debug mode. Okay, and when I run this, what happens is P1 port 1 is reset, and let us see whether the interrupt 0 is enabled. Yeah, interrupt 0 is enabled. Okay, if you see here, enable column. Now let me interrupt 0 is mapped to P3.2, so I will uncheck P3.2, so interrupt is enabled now. So it toggles the P1.5, because in our ISR we are toggling P1.5. okay, so let us see that ISR. Okay, I have to stop this debug session. Let me see that. Okay, in the ISR I am toggling P1.5. okay, now if I want to enable interrupt 1 as well, int1 as well, then my binary value should be in IE should be 1 as a EA 0 0 0, then 0 1 0 1. This is for int 0, and this is for int 1. So my hexadecimal value is going to be 85. okay, so 85. So I have enabled the interrupt, and I will write a ISR for int1. so int1 is the interrupt number 2. okay, so let us go back to our session. PPT session. This is interrupt 0, this is interrupt 1, interrupt 2. So I need to define this as int0 is the interrupt of type 0 in C programming, and int1 is the interrupt of type 2. So I have to write this as interrupt 2. Then I'm going to define another bit, okay, here called as swave 2. So let me say swave 1 and swave 2. In interrupt int0 ISR, I am going to toggle swave 1, that is pin 1.5, and swave 2 I will assign to pin 1.3, and in int 1 subroutine, int1 subroutine that correspond to int1 ISR, I am going to toggle swave 2. Okay, so let me repeat it. I have enabled here both int0 and int1. So int0 interrupt service routine is this particular method. So it is int0, which is of type interrupt 0. Okay, and here I am toggling pin 1.5. okay, and int1 subroutine is here, it is interrupt 2. okay, and here I am toggling pin 1.3. okay, so now let me compile this program. Okay, okay, no errors. Let me debug this program. Okay, now let us see, let us run this program. Okay, int1 and int0 are enabled and all the port pins have been reset. Now if I check on P3.2, int0 is triggered, and that interrupt will enable the ISR int0, which will toggle pin 1.5. so it is toggling pin 1.5. now if I check unselect P3.3, it will trigger int1. okay, when it triggers int1, it will toggle pin 1.3 here, because the ISR will toggle swave, where the swave is nothing but swave 2 and swave 2 is nothing but P1.3. so this is about the program to demonstrate multiple interrupts in C language. Okay, okay, in our earlier program we saw the interrupt processing of int0 and int1. Let me run the project. Okay, and let us revisit that program. Okay, so when I run the program and whenever I make P3.2 as low, that is int0 is triggered, so at that time you see that my P1.5 gets toggled frequently. Okay, so when I stop, when I make it high, it stops. When I make it low, it toggles. Now if you observe this, the interrupt is being generated when P3.2 goes low. That means int0 is a level triggered interrupt. Okay, so in order to make it edge triggered interrupt, we need to set some additional field. Before we write the program, let us go and revisit our TCON registers. In the TCON registers, in the timers session, we discussed about the higher nibble of TCON registers, and we said that we'll cover the lower nibble of the TCON registers during the interrupt session. Okay, now the lower nibbles of the TCON registers, there are IT0, IE0, IT1 and I1. IT0 and IT1 will make int0 and interrupt 1 as an edge triggered when they are set to high. So IT0 and IT1 will decide whether int1 and int0 are level triggered or edge triggered. So if I set IT0 and IT1 as 1, then int0 and INT1 are going to be edge triggered rather than level triggered. If I set them to 0 and 0, then INT0 and INT1 are going to be level triggered interrupts. Okay, so INT0 will decide whether INT0 is level triggered or edge triggered. Okay, now there are two additional fields, IE0 and IE1. IE0 and IE1 will be used only when IT0 and IT1 are set to 1. Okay, that means to say, if IT0 is set to 1, then INT0 is edge triggered. Okay, and the edge triggering concept is basically it will trigger the ISR whenever the edge makes a transition, whenever the INT0 makes a transition from a higher level to a lower level. That means it makes a transition at a falling edge. Okay, so you need to remember this. It is not at the rising edge, it is at the falling edge. So IT0, when it is set to 1, so whenever the INT0 pin goes from high to low, then the interrupt will be triggered and then the program will jump to the ISR. Okay, so when the transition happens from 1 to 0, when IT0 is set to 1, at that time the CPU will set IE0 flag to high. Okay, so similarly, if IT1 is set to high, then whenever the INT1 makes a transition from high to low, then IE1 will be set. At the same time, the program will jump to the ISR. Okay, so in order to make INT0 and INT1 as the edge trigger rather than the level triggered, we have to set these two bits to 1, IT0 and IT1 bits to 1. So that means the value of tcon will be 00000101. So that is equal to 05H. So let us go back to the C program and let me stop this session. Okay, and I will set tcon to 0x05. Tcon. Okay, let me assign tcon to 0x50. Tcon is equal to 0x05. Sorry, 0x05, not 0x50. So x should be small. Okay, and let me compile, save this and compile this and run this project. Compilation done. I'll go to the debug session and let me run the program. Okay, so currently the value of P3.2 is 1. So earlier we have said that the edge triggering works when the P3.2 makes a transition from high to low. So let me change it to 0 and observe the value of P3.5. When the transition of P3.2 happens from 1 to 0, then P1.5 should be set. So I will make P3.2 to 0. Okay, so P1.5 has been set. Similarly, I will make P3.3 to 0, that is INT1. So when it is made 0, then the P1.3 should be changed from 0 to 1. Okay, why? Because it is complementing here. Okay, so this is the interrupt service routine for INT1. Okay, so I'll make this from 1 to 0. Okay, so if you see here, P1.3 has been set. Please note, in earlier case when it was level trigger, when we made P3.2 and P3.3 as low, so the ISR was getting triggered very much frequently. Okay, because it was level triggered and it was toggling either P1.5 or P1.3 depending on the what interrupts were invoked. Okay, but now if you see, when the INT0 is low or INT1 is low, the toggling is not happening. This is because it only makes a transition, or the ISR is invoked in the falling edge, it is not invoked when the low value of the pins are low. So this is called as a edge triggering concept. Okay. Now, what is the advantage of edge triggering rather than over level triggering? The edge triggering offers you a better noise margin over the level triggering. Okay, let us go back to one of the problem that we had solved during timer. Okay, so this problem is to generate a square wave at P1.3 with a frequency of 10 Hertz. So if it is a frequency of 10 Hertz, then the time period is 0.1 seconds. So P1.5 should be high for 50 milliseconds and low for another 50 milliseconds. So we explained how we calculated the value of TH0 and TL0 during the discussion during our timer session discussion. So let us go to our keil session and let us explore that problem. So we are setting the timer in mode 1 and we are loading 4D and FD that corresponds to a delay of 50 milliseconds, and then we are running the timer and then we are checking whether the timer has overflown or not. Okay. Now let us run this program. Okay, and let us analyze this particular program using logic analyzer, output using logic analyzer. So let me stop the run. So my objective is to generate a 10 Hertz waveform. So the time period is 0.1 seconds. So let me calculate the time period. So I'll take this as a baseline. It is 0.3003 seconds, and for an entire one period it takes, this is 0.4003 seconds. So the time period is approximately 0.1 seconds from here to the this end. That means from this transition to this transition is 0.1 seconds. So the frequency of oscillation is 10 Hertz. Now when we see this logic, it says that J and B TF0 again. That means it will check the value of TF0, and then if it is not equal to 1, then it will keep on polling this particular logic, or this goes on executing this logic again and again till TF0 becomes 1. So this mode is called as a polling mode. And if you see here, to run these instructions again and again, we will keep the microcontroller resources busy, because the microcontroller has to execute these instructions again and again. So we are basically using the resources to poll a particular flag. Now in this session we will demonstrate how to use this program, how to change this program, and how to do a interrupt processing. Okay, so let me do one thing. So I will complement. Let me do one thing. Let me not reset these two flags, and let me remove this condition, and this I say AJMP again. Okay, I'll tell you why I'm doing this. So basically I'm setting the TH0 and TL0, and I'm jumping to itself again. So I'll remove these also, these two. These are of not of use in this mode, interrupt mode. Okay, I'll put this logic in 8000 memory location org 8000. Now what we are doing, we are changing the polling mode program to interrupt based program. So in order to do that, first thing that we need to remember is we need to set the interrupt enable flag. Okay, so what are the interrupts that we need to set in the IE? We need to set timer 0 flag. Now let us go back to our slide, earlier slide, and let us go back to IE flag, i.e. Register. Okay, if you see, if we want to enable timer 0 interrupts, then we have to set ET0 as high, as well as we have to enable EA. That means we have to enable all the interrupts as well as ET0. So it is, the value is 10000010. That means it is 82. Okay, so we have to assign IE register to 82. Okay, so let us go back to our keil and we'll say hash 82H. Okay, so we have enabled the timer 0 interrupts. We have loaded, we have made the timer in mode 1 and we have loaded the value and we have run the timer, and it is going to infinitely execute here. Now whenever there is a timer interrupt, it will go to the ISR. Now let us implement the timer 0 ISR. So it is org timer 0 ISR will be in location, which is the location, it will be in 000B. Let us confirm that in the IVT. So timer 0 interrupts, as and when it comes, it will jump to 000B. So we have to implement the ISR in 000B. 000B H. Okay, so what we will say is we will complement P1.5 here, and then we will reload the TH0 and TL0 here. Okay, so let me not remove it. Okay, I'll just move it. Okay, so let me explain what happens. Okay, and then I'll say RETI here, RETI. Okay, so initially I am setting TH0 and TL0 for a delay of 50 milliseconds for a time period of 0.1 second, and I'm running it, and I'm indefinitely looping in this particular loop. And when the timer overflows, since the interrupt is enabled, it will jump here, it will complement P1.5 and reload the value of TH0 and TL0, and again the timer will increment, and again the timer will overflow, and then when it overflows, it will come back to this service routine and complement P1.5 again. Okay, so that is about the interrupt processing of timer, but we are not yet done. So we will go to org0000 and we will say ljump start. Okay, org is 0000H, and over there we will say ljump start. Okay, so we have changed the timer program to an interrupt based timer program from polling based timer program. Okay, now let us compile this. Okay, let me exit from the debug mode. Okay, let me compile this and see if there is any error. Okay, there are no errors. Let me run this then. Okay, and let me monitor the waveform. Okay, so I'll stop my program execution. Let me again take the baseline. The baseline here is 2.151 seconds, and the transition again happens from high to low at 2.251 seconds. So 2.251 minus 2.151, it is 0.1 second. So this is the way the timer can be run using interrupts. Okay, now let us see the power of interrupts. Okay, so in the earlier program we were able to generate a square wave in P1.5. Now let us say that we want to generate a square wave in P1.5 as well as P1.3 simultaneously. Now we can we do this in the polling mode? Yes, we can do that in the polling mode, but the processing logic will become complex. So to simplify this, we can use interrupt based programming. Now if we want to do multiple tasks, interrupt programming becomes simple and more efficient to handle. Okay, so let us say that we want to generate square wave in both pin 1.5 and pin 1.3, and pin 1.5 it should be at 10 Hertz, and in pin 1.3 let us say that it is of higher frequency than 10 Hertz. Okay, so if we want to do that, we have to enable the interrupt. We have to use timer 0 to generate 10 Hertz. Okay, and we have to use timer 1 to generate some frequency greater than 10 Hertz. Okay, so let us see what all bits should be set for timer 0 and timer 1 in interrupt enable table. In interrupt enable table, ET0 corresponds to timer 0 bit and ET1 corresponds to timer 1 bit. So if we want to enable timer 0 as well as timer 1, we have to set both to high. Okay, so EA should be high, ET1 should be high, and ET0 should be high. So the value is 1000 1010. So that is 8A. So IE should be set to 8A. Okay, and we have loaded T mod as is equal to 01. That means timer 0 is in mode 1. Now let us also make timer 1 also in mode 1, and we have preloaded loaded the value of TH0 and TL0. Let us also load the value of TH1 and TL1. Let us now use some arbitrary frequency in other pin P1.3. Let us say that for that frequency the delay is 0 BB. Okay, in TH1, and TL1 it is 0 FD. Okay, now when the timer 0 overflows, it will jump to 000B. So let us go back to the IVT interrupt vector table. When timer 0 overflows, it will go to 000B. When timer 1 overflows, it will be going to 001B. So we have to implement ISR at 001B also. Okay, so let us implement ISR in 001B. Okay, so when I do this, so my objective is timer 0 should complement P1.5 and timer 1 should complement P1.3. Okay, and timer 0 corresponds, so the frequency of oscillation at P1.5 is 10 Hertz, and P1.3 is something greater than 10 Hertz. Okay, so for that I said that I will choose arbitrarily the value of TH1 and TL1. So I will set TH1 and TL1 with some arbitrary value that will generate a frequency greater than 10 Hertz. Okay, so let us see. Let us reanalyze this program. So at 0000, I'll jump to start. At start, I am enabling both timer 0 and timer 1. I'm setting both timer 0 and timer 1 in mode 1. I'm loading delay of corresponding to 10 Hertz in T0, and loading some delay that generates a frequency greater than 10 Hertz at T1, and then I am running TR0. I'll also have to run TR1, timer 1. I have to run both timer 0 and timer 1. Okay, and whenever the timer 0 overflows, it will be jumping to 000B, and I have implemented the ISR to complement P1.5 and reload T0 to 4B FD. And whenever the timer 1 overflows, it will jump to 001B, and I will complement P1.3, and I will reload the value of 0BB. Sorry, I'll reload the value of BBFD in TH1. Now let us recompile this program. Okay, and let us see if there is any error. There are no errors. Now let me run this program. Okay, before running it, I need to check whether I need to set up logic analyzer. Okay, now in the logic analyzer, let me set P1.5. I need to plot the waveform at P1.5. Okay, and the maximum value of P1.5 is 2 and the minimum value that I anticipate in P1.5 is 0. Okay. At the same time, I need to set P1.3 because I need to plot the waveform of P1.3 as well. And here the maximum value I'll set it as 2 and minimum value as 0, and I will use blue color. Okay, and let me close this and run the program. Okay, so wait a minute, I have not changed P1.5. if you see here, the value doesn't look good, so let me go to the setup again. Okay, it has not changed to 2. Okay, so let me do that again and let me run the program. Okay, good. Now we are all set. Now if you see P1.5, so this is the P1.5, it is oscillating at a frequency of approximately 3.85 to 3.95, that is 0.1 second is the time period. So the frequency of oscillation is 10 Hertz, and P1.3 we have set some arbitrary value of delay, and that has caused P1.3 to oscillate at some other frequency. So the interrupt will allow us to use or will allow us to do multiple processing in 8051. So this in this example we have restricted ourselves in using timer overflow, timer 0 and timer 1 using interrupt. Now we can also work out on other aspects as well, like we can create an interrupt for serial mode communication. We can create a interrupt for external interrupt. So we can do multitasking using interrupt, which will be very much difficult or nearly impossible when we are using polling mode. So this is the advantage of interrupt based processing.